Wilson loops and started to discuss the Wilson loops, and today we will see some variations of this idea. So the idea was that in order to test our theory, our gauge theory, we need to measure to introduce some correlation functions to decide which behavior of these correlation functions corresponds to which. And the natural thing in the superfluid case was just the correlation functions of the type e to the I phi of 0 minus phi of r. We discussed this. And we actually have, we can also write it down as e to the integral d mu phi dx mu. And as we go to that's when the basic dynamical variable was the phase phi. Now the basic dynamical variable in gauge theory is a mu, and we said that the analog of this difference would be integral a mu dx mu, and the analog of this formula will be e. Here we integrate over the open path connecting points 0 and r. Here we integrate over the open surface. We just take the contour. So this depends on r. We integrate over the surface for which C is our boundary, and we have the function w of c, which, as I started to explain last time, which measures actually the strength of interaction between two charges. And not only that, we actually will see today that there is some interesting version of this construction of this object, which is appropriate for non-equilibrium situation, like the charge radiating stuff and experience radiation friction. And there is an interesting version of the Wilson loop which we will come to. But at this point, I already made this comment that in order to the reason why this thing is independent depends only on r, not on the path, is the quantization of vortices, and this is quantization of magnetic charge, because vortices, magnetic charge, dislocations, these are so-called defects, which, roughly speaking, in some crude sense, they say they violate the Bianchi identity, so that one way of saying is that they are multivalued, and because of that this is non-zero. But that's not a very good way. And so you have to be careful in applying theorems of vector analysis, but probably a better thing is to say that just the field strength, so to say, if you introduce d mu phi, it satisfies corrected Bianchi identity. And there is a okay. We shall return to this in a moment. And the key point is to introduce the static particles. Why these Wilson loops? What they mean? you introduce the two static particles. As we discussed last time, these are these static particles are the limit of quantum particle it's the limit of high mass, the high mass limit. And we said that the propagator for a relativistic particle actually goes into epsilon plus I0, where epsilon, where we denoted P0 m plus epsilon. So if you keep one more term, you get the term P squared divided by 2m, and that would be non-relativistic but quantum particle, which propagates according to quantum mechanics. But in the limit of infinite mass, this term actually disappears, and that means that the particle is strictly, in this case, the green function is simply, you can of course obtain it from the green function here in the with the proper limit. It's just step function multiplied by delta of x. Since it's independent of p, it gives you the delta function when you make Fourier transform. So these are static particles, and you can actually describe it, we will need this, by introducing the field for static particle. And the Lagrangian corresponding to this propagator will be simply psi dagger of t d psi dt. That would give you the green function like that. And now suppose that your charge, this is the propagator of the charged particle, and we want to describe some Feynman vertices. So suppose we have some scalar potential A0 of x, or x and t in general. Now, and actually I think I will do it for the general case, it's simpler. And now I want to write down the interaction of psi, the term psi A in this non-relativistic limit. And I assume I want to write down for the case when my test particle, my heavy particle, not simply sitting at a particular point, but actually is guided along some particular contour. So the question is, I think it would be probably the right thing to do would be first to solve it for the particle sitting at rest at the origin of coordinates. So what would be, suppose you add electromagnetic field. We know how to couple it, so what will be the change of the Lagrangian? So the answer. If I want to calculate diagrams of this type, this is photons, and I want to calculate it in the heavy particle limit.
Psi dagger E0 psi.
Yes. And A0 depends on x and t. So which argument should I put here? What is the argument of?
Should we start x equals 0?
Yeah, since it describes x equals 0, it will be at t and 0. And now we will generalize it a little bit and write down, introduce the heavy field, which corresponds to the particle. So here is the trajectory was arbitrary t x equals 0. Now suppose I have some general classical trajectory t of s is the proper time, and x of s. And I want to introduce the field. I will take psi dagger this time of s, d psi ds. But the question is, so that's x mu. The question is, how shall I replace this term? What to write?
First,
Yeah.
question, why is defect ds? Parameterize.
I want to say that in the frame where the particle rests, I have just this static particle where s is the proper time. So it's just in the rest frame of the psi depends only on the properties of the particles, and because the particle is located on the particular one-dimensional trajectory, so the field of this particle is just this one. It's simply replacement. It's, if you wish, it's a conjecture which we have to verify. Here we derive this from the propagator. Here also you can derive similar things from the propagator. But the meaning of it will be clear. It's better to first try to write something reasonable which replaces this term. And then you will see the meaning of it. So I just want to go from the particle which propagated along the straight line, and this line was, I could go actually by step by step. For instance, here the particle propagates in time only. Now in some accelerated frame, it propagates along some straight line, and what do you think would replace this term? And then the next possibility is it propagates along some arbitrary contour. So we looked at these three possible situations. So yes, which invariant? Well, actually, the answer, yeah, but the problem with what you want to say is that it doesn't reduce to this thing in the answer should reduce to this end, to this thing. Huh?
I'm thinking which invariant we should take in order to introduce to this.
Yeah. Well, the answer is this is creation annihilation operator, and we actually have a mu of x of s dx mu per dx mu over ds. So, and we integrate the whole thing over s. This, by the way, is simply if the particle is present, it's 1. If the particle is absent, it's 0. So that just describes the particle on the. And that's the way you have in quantum mechanical, the Feynman propagator is the sum in quantum mechanics, the propagator is the sum over paths connecting 2 points. And in the limit, when by some external field you keep particle along a particular trajectory, and quantum fluctuations are small, the key point here, the reason why it all makes sense, is that quantum fluctuations are negligible in the limit of large M. Quantum fluctuations are here in this term. And it's because of this term you have uncertainty principle and things like that. If you have no p square, then the particle can be located at a particular trajectory. And we will see actually very soon today that how this works in the case of accelerated particles and so on. It's just the way to treat the usual Feynman diagrams. You have the usual Feynman diagrams, and in general you substitute, instead of this line, you substitute the sum over trajectories. And if one trajectory is singled out by hands, literally you guide the particle with some external force, you guide it along a particular trajectory. Then instead of Feynman propagators, you substitute this reduced propagator, which gives you basically the Wilson line multiplied by something trivial. Now, yes? Huh? What I mean is, you see, what I mean is the best described in the case of particle at rest. We have p minus k, k, p, and this is integral d for k, p minus k square, minus m square, 1 over k square, and so on. And then you do this, you approximate, instead of this guy, when p square tends to m square, you approximate it by taking p0. Well, you basically reduce the propagator to this one. And that's it.
You call it reduced propagator.
What?
You called it reduced propagator.
Yeah. Reduced is a non-relativistic propagator is this. When I replace it, it corresponds to the statement that in my approximation, the particle doesn't, it's a static approximation. The particle doesn't propagate along arbitrary paths, but it simply sits at rest. This is a static particle. And this guy is a photon. We don't have to assume that it's not non-relativistic. Of course, it's massless. And so it is. Now, this will be useful, and we will actually see, as I said, several versions of it today. It's just the simplest version of the Wilson loop. But it's good. Before we go to more complicated things, let's understand what it means. If we take two particles separated by the distance r, which propagates in time, then the amplitude of such propagation will be proportional to e to the, in the Euclidean time, it will be proportional e to the minus e of rt. And what we will find out is that, let me call it f. What we will find out is that f is actually proportional to e to the minus some constant, a minimal of c. where A minimal is a surface, a minimal surface for which the boundary is the contour C. And of course, in this case, minimal surface is means that you will get the surface is just flat. So you will get, if you have this, the statement, let me formulate the statement. If we haven't yet explained this, but this Wilson loop then E of R is proportional to R. And in fact, you cannot get, it's impossible, would be impossible to get some power of R. It would immediately contradict causality, as I mentioned last time, that when you have, I mentioned it in one dimension. In one dimension, if E is proportional to R, then you cannot send the signals with faster than light. But if E is proportional, say, to R to 2/3 or something, then you indeed can send signal faster than light, so it cannot happen. And correspondingly, it corresponds in general to the fact that you get a geometrical object here, the minimal area, or you can get a perimeter or some curvature, but in all these cases, you will not, you will get either E of R proportional to R or E of R going to 0. By the way, what will be the, if you have Coulomb interaction, what kind of answer you will get for this picture, for this amplitude F? It will be T divided by R answer. And actually, you can, it's interesting to derive it from you have to take the integral, the F would be integral dt1, dt2. You exchange the quantum, and you have a propagator which is G of R, T1 and T2, and that will give you the Coulomb interaction. It's photon propagator, which I will call D. It will give you the Coulomb interaction. That's a good exercise to derive it this way. So it's simply, again, it's simply good old Feynman diagrams, but in non-relativism, when you replace certain lines when you assume that certain lines are fixed and not really fluctuating as they should in quantum mechanics. Okay, but now the question is why it is a natural answer, why it's a minimal area, and what it means. And actually, what would be the analog of this statement in the superfluid case? The statement that you have this area here. What would replace this statement in the first case? Yes, it will be. It's simply the statement that G is proportional e to the minus mu r, which is characteristic for which phase of superfluid? Yeah, it's a normal phase. It's when you accumulated enough defects in the system so that they actually prevent the kill the correlation. So the Coulomb phase, this is called the confining phase. This is called the if you have this simplest one photon exchange, it's the Coulomb phase. And the Coulomb phase corresponds to the normal phase of the superfluid and excuse me, to the superfluid phase of the superfluid, while confining phase corresponds to the normal case. That's in order to get confinement, you need a finite correlation length. This correlation length simply means that quarks are localized; they cannot go far because everything falls exponentially. And I will give you the idea how this is derived. How you get this. We will need this. Okay, I shall write it down later again. Notice the following simple thing, that if you have the action which was let's again do it in parallel here and here. I will give you first a pseudo derivation. Suppose for one moment we take b mu equal to d mu phi, and we write down the correlation function as the integral b mu dx mu from 0 to r. And the Lagrangian is simply b mu square. Okay, so what would be the answer? And suppose for one moment I forget about this constraint. I take b mu arbitrary. So suppose I integrate over arbitrary b mu. I have the action. I have the action which is quadratic in b mu square, and I want to calculate this thing. It's a Gaussian integral, so it's very easy to get the answer. Actually, yes. What is the correlation function? B mu of x, b mu of x prime. In order to calculate, it's how it depends on x.
1 over x.
Be careful here.
How many dimensions?
Any number of dimensions. B mu is,
X minus x prime?
yes, it's simply a delta function, because I forgot about this constraint temporarily. Now, a very simple mnemonic rule to calculate a Gaussian integral is that you take, this is a Gaussian variable, so we expand it up to the second term. Dx mu, dx mu. So we expand it up to the second term, calculate, and then exponentiate back. So it's approximately e to the minus 1. And this time we get the exact answer with Gaussian integrals. Now you see that what we get is the length is the minimal length because this is a delta function. Without delta function, it would be a square of the length, but it's the delta function dx prime. And I suggest that you do the following simple, nice geometrical calculation. Suppose you have four-dimensional delta function, and you integrate it. Then prove that it is, and you integrate over, so it's a double integral over some contour. Prove that this is a minimal area, minimal length, which depends on, suppose contour goes from 0 to r. It's proportional to minimal length, in this case simply to r, but it could be done in arbitrary geometry. So this double integral is the length, and we get this result, and we get it by making a wrong assumption that b mu is an independent variable. I shall return to this wrong assumption and correct it in a moment. But before I correct it, I want you to figure out what will happen if I play the same game here. Namely, the game which I want to play is the following. Yes, that's what I want to do. I want to take f mu as an independent variable, and I want you to figure out what the Wilson loop will be in this case, how it will behave at large. Yes. Why do you think so?
Because we will have like a f mu and f lambda rho, and they propagate the delta function.
Yes. Yeah.
One integral we will have from the delta function, and we will have second integral.
Yes. Actually, another interesting exercise is that if you have the contour and you have the integral delta of x minus x prime d sigma mu of x d sigma mu of x prime, and this is the four-dimensional delta function, this will be proportional.
But they have different indices.
No, the same indices, because you have f mu square, which means that indices are.
Okay, because
So you'll have e to the minus area, minimal area of thing. It's an interesting fact that you can represent minimal area like that.
No, this is like e to the.
Oh yeah, sorry. It will be the area. The area plus corrections, plus you have to regularize the way to where this is the exercise I suggest. You represent the delta function. It would be nasty singular thing if you do it directly. You have to introduce first the smeared delta function, which you can take whatever you like, any smearing you like. The best, the most convenient smearing is this one. It's e to the minus x prime square divided by 2 epsilon and 1 over epsilon to some power, to the needed power. The thing which in the limit epsilon to 0 is the heat kernel. It's just the heat kernel as the green function for the diffusion equation. As epsilon goes to 0, epsilon plays the role of time of this diffusion. As epsilon goes to 0, you get the strict delta function, and it's pretty easy to evaluate. Well, it's not so. Actually, this formula, it takes some not thoughts, but some calculations to derive it. I will tell you one more interesting thing, which is not related to the lecture directly, that if you take in 4 dimensions, that's one invariant thing which you can write. But there's also another combination of the same type, which is what? Well, we can write down another object, let's call it nu, which is the integral delta of x minus x prime d sigma mu of x d sigma lambda rho of x prime and epsilon tensor. And let's integrate this guy over two-dimensional surfaces. And there's a, so you take x mu as a two-dimensional surface, you perform the integration, and now guess, maybe it's unfair question, but try to guess what, it has a fantastically interesting geometrical meaning. Try to guess which one.
The number of intersections.
Yeah, it's the number of intersections in when you have two-dimensional surfaces in 4 dimensions. They generically they intersect across points. Across the points. So just like when you have two curves, then generically two curves intersect in a point. In the same way, generically two-dimensional surfaces in 4-dimensional space intersect over the points also. And now you count algebraic number of these points, and that gives you this intersection number. And so you guessed correctly, but now make another guess how to prove it, where it will come from, why it should be related to this integral at all. Well, you see, intersection points, intersection occur when you have 2 points. Psi is this pair. Then x mu psi is equal to x mu theta. That's the intersection of this thing. And the delta function clicks each time this happens. And the remaining thing will be some trivial Jacobian which you can easily evaluate. So which will give you plus or minus 1. I will not go into that further, it's not really mine. But just good reason. It's quite beautiful result.
And what is the meaning of minus 1?
Oh, you have it's the orientation under which you have two surfaces which can have different orientations. So each point intersects. You have, the point is that you have on each surface you introduce orientation, 2 vectors. Orientation is the ordering of 2 vectors. And then when they unite you get 4 vectors, and they can have either, in some intersections, they have orientation +1 and some orientation -1. I stop this subject. It will take us on another long path, and it's not my intention. Now let's try to see what we concluded, is that confining regime is, in a sense, related to the forgetting about Bianchi again. And now you can make the conclusion why it is natural. I can tell you what will. Remember, we said that we have the Bianchi identity is sum of QA delta of vortices, and analogous thing with monopoles for F mu, namely we write down d mu f mu lambda plus etc. plus cycles is equal to the sum over monopoles. And now, we wrote this formula before, but now I want you to relate it to the fact that when you completely forget about the constraint on B mu, you get immediately the area law and the length law for superfluid. So that actually gives some qualitative idea what to expect from monopoles and.
So if you would have many monopoles, that you can make any.
They basically, that's right. That they somehow can imitate this any what is this any left-hand side, and so when you have freely produced monopoles with finite density, you can expect that Bianchi identity will be either removed or weakened. And in this case, you would expect the area law. And now I'll tell you very briefly, because we have more interesting things to discuss, very briefly how this is being calculated. This, in fact, this qualitative idea is supported by real calculation. Namely, when you have when you are in the plasma phase for the monopoles, that means they are flying more or less freely through the system, in the system. They obliterate the Bianchi constraint. And you get the confining regime. Or another physical analogy is that, which I already mentioned before, that when you have many impurities in the system, it localizes charges, localizes particles, because particles are actually influenced by a random potential produced by the impurities, and if there are enough of them, it cannot propagate. It becomes exponentially localized. So now how this is, that's the general idea, but I will quickly give you some, you can find detailed calculations in some books. I will simply quickly give you the idea of the calculation. We basically.
Question is.
Yeah, go ahead.
This minimal line formula, does it depend on dimension 4 or not?
Oh, actually, I think it would be better to have the delta function with dimension 2. L, you see, that's good that you asked this. We actually said that there are special dimensions. They are not critical dimensions, but there are special dimensions for superfluid, which is dimension 2. It's the dimension in which the defects are point-like. The defects in this case are just vortices. And it's the simplest case when vortices are important, when they are point-like. In 3 dimensions, we have monopoles. In 3 abelian dimensions. We have also point-like defects in 4 dimensions, which are non-abelian instantons. But they are more complicated. Where, in 4 dimensions, we have 2 types of instantons. We have either loops of magnetic monopoles. Well, maybe I shall return to this.
This formula is true for any dimensions?
Which one?
That one.
Yes, it's true for any dimensions, but the thing, what will be different is epsilon dependence.
Right.
Epsilon dependence will come different.
Really
This formula is only for 4 dimensions. You can, but, what would be a superfluid, so to say? And this is the formula for gauge theory, nature for gauge theory. Now, what would be the superfluid analog of this formula?
What do you mean by superfluid analog?
I mean, suppose here we deal with surfaces. In superfluid case, we deal with lines. So, what would be the formula?
But we already wrote it, no?
No. I wrote it for the length, but I mean the formula with the epsilon tensor.
I see.
You see, there is also the formula
Epsilon
mu, x mu dot, dx mu, dx prime mu, delta of x minus x prime. It's also proportional to the self-intersection, to the intersection of the curves. And another thing which you can easily derive from this.
But here it's only in 2 dimensions.
Yes,
No,
yes,
no.
yes. These geometrical formulas, they are true only for 2 or 4. So you have to change, you need special dimensions. You can use also this formula to derive the quite remarkable fact that if you have a curve here in 2 dimensions, and you measure the angle of the tangent, then delta phi divided by 2 pi will be mu plus 1 modulo 2. It's this is the formula used for one of the solutions of the Ising model, and it's quite interesting, and it has high dimensional analogs and so on.
So in 3 dimensions we cannot write now this already.
In 3 we have to do something else. In 3 I can tell you what, there is also interesting formula in 3 dimensions, but it would drive us. The formula, I will just say that in 3 dimensions there will be formula related to the Chen-Simons action. Let's not go into this. So, how these things are really calculated? The calculation is actually simple. You take a loop, and you first calculate the contribution of one monopole, and you see that this contribution is, we saw last time, this contribution is simple, is easy to calculate. Namely, we take the surface for the contour C, monopole is here, and we, instead of calculating a mu dx mu over the contour, you use the Stokes theorem and you calculate the flux of B ds or d sigma over this surface with boundary in C. And the B, or the A for the monopole there, it's complicated, it contains this tail explicitly and so on, because it's the vector potential of the solenoid. So it would be a little messy to calculate this thing, but B is very simple. B is just x divided by x squared, x cubed. And so you have the answer is the dimensionless integral, which is just the solid angle. The integral is x minus y, x minus y cubed d to sigma y. and that's the contribution of a single monopole to the contour. And you see already that when we write down, when we consider the plasma of monopoles, you will simply have contributed, when you have many monopoles, the contribution will be simply the sum of all of them. So the contribution of the nth order will be just something like sum of the QA B of XA minus Y integral into sigma Y. And you can go further. It's clear that we said that before that the monopoles form a Coulomb plasma, and that I will not be, I think, deriving now, that in this plasma, this surface is a double layer. It's like introducing the double layer in the plasma and calculating this double layer energy. It's all semi-classical and simple. You use the Debye equation. The potential in the plasma is just sinh, some constant m square, sinh of phi, and plus this source, plus this external density coming from this surface. And when you perform now, do you remember why sinh phi? I don't want to go into details, but I want you to understand what comes from where.
Different charges.
It's different charges, and e to the phi is just the parametric formula. In the mean field approximation, the Debye approximation in plasma is that you have the Poisson equation, and rho is in real plasma it's e to the minus phi divided by temperature minus e to the plus phi divided by temperature. So that's the origin of sinh. Crudely, the origin of external density is this. Is given by this formula, and the details you can read, for example, in my book, the real calculation. And we have to, so that's but as I said, the qualitative meaning of this result is that the relaxation of the Bianchi identity, that those monopoles, they relax. Yeah. Actually, that's very similar to, well, there's in 2 dimensions, when we have superfluid in 2 dimensions, it's slightly different than this 3-dimensional case. So let me start again. In 3D, Debye screening means that monopoles can be treated semi-classically, and they are free. They are flying. There is always a free moving charges in this plasma. As a result, free monopoles, free moving monopoles. They are not free, they interact. they correspond to confinement of electric charges. In superfluid in 2D, that's different from 2D because in 2D, at very low temperature, vortices are actually confined at low temperature, confined vortices. That means superfluid. But there is a critical temperature, the temperature of phase transition, after which our vortices become free and we have confinement or normal phase exponentially. This is characteristic for the normal phase. So, and what I said refers to gauge theory in 3 dimensions and superfluids in 2 dimensions. Now, I will tell you briefly what happens in higher dimensions. And we will go to, well, we will basically continue this, but some very different aspects of the problem will be discussed. What happens if you take this picture? Well, I suggest that you have to go through. It's fun to really derive these equations and to precisely learn how this external density, what external density to prove that this is a double layer and so on. So that I leave to you. But let's discuss what happens, for example, in gauge theory in 4D. If we talk about abelian gauge theory, or it's sometimes called compact QED, then what we will find is that vortices, the defects are now line-like because the simplest defect is simply to take 3D point, which propagates in time. We add, time is imaginary, and we add the 4th coordinates. So instead of point-like defect, which we call monopole, now there will be a line-like defect.
But why we cannot make point?
What? Okay. That's purely geometrical fact that.
So you mean instead of one delta function, we'll have that theta function, right? Instead, I mean, we usually have delta functions.
Yes.
Here we would have.
You see, if you look at this sort of, yes, if you look at this formula, you see that it's a rank 3 tensor, rank 3 antisymmetric tensor, 3 form, for the gauge theory. On the right-hand side, we have 3 in 3 dimensions. If we have 3 form in 3 dimensions, that means that those defects are point-like. But when we have 3 form in 4 dimensions, we don't have in 4 dimensions this tensor. You see? So you cannot have point-like defects. Instead, you have, when you introduce these propagators, you have those propagating in time objects, which are nothing but what they physically mean. We had those magnetic monopoles which were point-like in space-time. That's why they're called instantons. They have been localized both in space and in time. In 4 dimensions, they're not localized in time anymore, at least when you draw it like that. Then what corresponds to these magnetic monopoles in 4 dimensions? What's their physical meaning? If you have an object which is one-dimensional in space-time, what do you associate with this object?
Particle.
Huh? A particle, because in 4 dimensions, those magnetic monopoles become particles. They're real particles, which never been found, but which must be present. Well, that's a little down there. In any case, we now have, if we treat it as a Euclidean partition function, we now have to sum over all possible loops of monopoles. So we have in 4D, we have closed loops of these particles, which means these particles are spontaneously created and annihilated. And at some point, the standard spiral's argument tells you the following. It tells you that, first of all, if you have a monopole of the length L, if you have the loop of the length L, then the contribution to the Wilson loop will be proportional to e to the minus c L. Its energy will be, it's inversely proportional to the coupling constant, E0, and there's some constant, and it's proportional to the length, which is to say that the contribution to the action is very much suppressed here. If E0 is small, you will have only very small loops, and they will not, their disordering effect on the Wilson loop will be negligible. So the first part is kind of negative, namely that if we have very low temperature, in this case, the loop or very small coupling, very small charge, small coupling constant, these loops cannot disorder the Wilson loop. You can make an estimate, but it's intuitively obvious that they will not lead to confinement. But if you increase E0 at certain value of this coupling constant, those loops become larger and larger and become infinitely large. So why is that, by the way? Why what really happens in this system is that there's a critical charge. So for the charge smaller than critical, there's no confinement, but there's a phase transition to confinement at some critical charge. So what is the argument, qualitative argument for that?
Entropy factor.
Yeah, entropy factor, exactly. This logic is used all over the place. The contribution will be, actually, there's exponentially many contours of a given length, and you see that you expect from this crude argument, you expect some critical point, and you can prove that it is indeed there. After which, the number of these lines becomes infinite, and they start to be creating all over the place, and they confine electric charges. Now, if we treat, and now a question to you, if we treat these magnetic monopoles as particles, here I took the view that they are one-dimensional instantons. Just in the same way, I could say, but
So it's very similar to polydimensionalizing.
yes, it is very similar. As I said, this is the Piles argument, which is. But what I'm now asking a slightly different thing, namely, let's treat these as particles. So we have a system in which we have magnetic monopoles. We can describe by some new field, chi, which corresponds to magnetic monopoles. And those monopoles, they are irrelevant at small coupling, but there's a phase transition which makes them relevant, according to this entropy argument, Piles argument. The question is, this phase transition has a very simple meaning in terms of the fields of magnetic monopoles. And then I'm asking you to figure out what really happens when those loops begin to condense. What happens to particle? What kind of familiar phenomenon it's related to?
Requires an expectation.
What? Yes, it's basically Bose condensation of chi's. When chi's acquire an expectation value, you have a condensate of monopoles. And in this condensate of monopoles, electric charges cannot propagate. There's, when you have infinite, that in this geometrical language means that there are infinite loops all over the place, and they destroy and they give large contribution to the Wilson loop and create area law. So that's what happens in 4D. And it's still unexplored. It's interesting that in quantum electrodynamics, in pure electrodynamics without particles, you have a critical point, how it's related to the fine structure constant. And another question which is not answered, as far as I know, is how it clashes with the Landau pole. There are plenty of questions, and they are not purely theoretical questions, because we do know that the standard model contains SU2 cross U1. So what we are discussing is directly applicable to U1. We do not know whether at very high energies there will be what is called grand unifications. It could be, but it's quite legitimate at this stage. We don't have a single evidence for it so far. So it is not crazy to consider U1 as separate entity described by some compact QED, and to study what will happen with a Landau pole when you take into account those monopole condensates and so on. I think there is still there will be some discovery, some surprises here, but we'll see. In any case, it's an open thing, open area. Well, we also see that if we need, if we look at the, there's, okay. There is also, when we go to four-dimensional case, as we did here, we also have point-like instant, non-abelian instant points, but their contribution to the Wilson loop is, and their relevance is much more complicated. It's, they don't directly lead to confinement in this way. However, in supersymmetric theory, you can sum over the instantons. There are methods to get the sum over instantons and to see that indeed they lead to confinement along these lines. They somehow become responsible for this for the condensation of magnetic monopoles. But generally speaking, the problem of confinement is still not solved. And one of the approaches to it would be gauge string duality, which I will probably discuss next lecture. Now I want to tell you about some other aspects of these Wilson loops, etc. Some non-equilibrium aspects of this Wilson loop.
So what is the connection to superconductivity? Is there a connection?
Connection between.
Like a 3D gauge theory?
Oh yes, of course, yeah, good question. Right, there is a direct connection. If you start in 2D, the defects are point-like vortices. If you start in 3D, consider superfluid in 3D, then there will be precisely the same picture. And it is well known that the passing from the phase transition from superfluid to normal is related to creation of vortices. And vortices in 3D are smoke rings, closed lines. So indeed, in the three-dimensional superconductor, which we have in real life, you have vortex lines, quantized vortex lines, and it is their condensation which leads to breakdown of superfluidity. I shall also mention that we derived the criterion for breakdown of superfluidity, that the velocity of the moving body is less than speed of, it becomes less than speed of sound. But in fact, in real life, it is not, under this condition, you will start creating sound excitations. Okay? When it's in this is the, when you go beyond speed of sound, you start creating Cherenkov radiation, so to say, in certain fluid. But in real life, it's not the sound waves which breaks. That would lead to a very high critical velocity. It's what experimentally people let superfluid go through capillaries and measure critical velocity. In fact, what really defines critical velocity are vortices. What is created are vorticity. It's very much so. It's very similar.
So why is 3D superconductor related to 4D gauge theory and not 3D gauge theory?
Say it again?
Why is the 3D superconductor related to 4D gauge theory?
Oh, because you see, because of the structure of the anti-density, we have here dimension 3. You see, in gauge theory, we have vector potential A mu, which is one form, first rank, rank 1 tensor. We have field strength F minimum, which is second rank tensor, and we have the Bianchi identity, the left-hand side of which is the third rank tensor. The defects are point-like if dimension of space is equal to dimension of the Bianchi identity. Now, let's do the same thing in the superfluid. We have 0 form phi, which is our basic variables. We have d mu phi, which is the analog of F minimum. And the analog of Bianchi identity is, you see, you form things like that, which is the second rank tensor. So you conclude that the right-hand side of Bianchi identity is the left-hand side is the two form for the superfluid. Now that's, so here I made the comparison between 2D superfluid and 3D gauge theory. Now, as we go to 3D superfluid and 4D gauge theory, in both cases the defects will be linear, will be one-dimensional. And that's what, why that is the analogy. See? So, if you go, for example, if you imagine the system which occurs in string theory, which is described not by two forms, but by three forms, then the critical dimension, the special dimension will be 4, and we'll have defects of dimension 4. What we will, this probably running out of time already, but what we will start discussing tomorrow is some other version of the Wilson loop, which is which occurs when you ask the question. Actually, the question which we will be asking tomorrow is this one: how to, if you have a test particle propagating along some contour C, what we can ask how much radiation it loses. So far, we looked at the static Wilson loops, which measure simply the transition, the total energy, the Coulomb energy of interacting between particles. But there are other Wilson loops. Wilson, it's not really Wilson loops, but something similar, which measure the radiated energy and which play quite an important role, I think. But let me stop here.